Minimax rule. This is an extension of the discussion on Maximax and Maximin rule. I'm going to use the same problem that I used, the cookie problem, that I used in the other two rules. So it would be recommended that you watch the other two rules prior to watching this particular video, because it would help you understand the problem better. You can get a better idea about the exercise that we're about to do, and the difference, of course, between this rule and the other two rules that we had already discussed. The videos are available as links on my channel. Please watch the video on Maximin and Maximax rules prior to watching this video. Okay, that being said, what is the Minimax rule? The Minimax rule is the most optimal rule in many cases when compared to any of the other decision rules, and the idea here is that we take the minimum of the maximum, hence the name Minimax, of not the reward matrix, rather an opportunity loss matrix, which is obtained by finding this particular quantity. So what we'll try to do is, for every given state, which would be in my columns, for every given state I'm going to find the maximum reward that I could get for a particular state. And after I find that maximum reward, which is denoted by maximum Rij sub I, which is R sub j star, and after I find that maximum, I subtract the reward matrix elements from this particular value. And when I do that, I end up getting what we call an opportunity loss or regret matrix. And it's quite straightforward. The Minimax name rather comes from argmin of max. First you find the maximum of the regret matrix, and then you take the minimum of the maximum regrets that you would have. Hence the name Minimax. As strangely, the only difference, although it is called the Minimax rule, the key difference between this rule and the other rules are the other rules act directly upon the reward matrix, but in this case it actually acts on what we call an opportunity loss or regret matrix. So I'm going to use the same problem. If you don't follow the math back there, if it's all Greek to you, you could just wait and we'd get to the problem and it should make better sense. It's the same bakery problem that we talked about in the other videos. We know that the cost to make a cookie is 50 cents, the sale price of cookie is $1.50. The bakery sells cookies by the dozen. On any given day, a maximum of 5 dozen cookies can be sold. The states are equally likely. That someone would buy 1 dozen cookies, 2 dozen cookies, 3 dozen cookies, 4 dozen cookies. They are equally likely. And of course, I'm not considering the case where you won't sell any cookies at all. So we found the cost of a dozen cookies is $6, and the revenue from a dozen cookies is $9. And they're all equiprobable. That is my assumption, that the states are equiprobable. They happen with the same probability. The objective is to choose the best action A1 through A4. And I showed in the other video how to find the reward matrix, and we completed the reward matrix, and this is what we have. Now, this does not change for any of the rules. Finding the reward matrix is crucial to find a decision. But when it comes to Minimax rule, this is not sufficient, and we have one more step. The step is, for each of these states, I have 5 states where I sell 1 dozen cookies, or 2 dozen cookies, 3, 4, or 5 dozen cookies. For each of these states, I have to find a maximum reward possible across all actions. So if I picked state S1, I'd like to know the maximum reward possible across all actions for the state S1. So the maximum of the numbers that I see is a 3. So the maximum reward across all actions from the reward matrix is 3 for the first state. Now, which is what we call as R1 star in the original formula. We called it as RI star, and RI star is what we actually have. Excuse me, RJ star is what we actually have across all i's for every state. It is RJ star, and all we're trying to do is we're trying to find the RJ star across all states. So for the second state, which is the second column, I would like to find the maximum reward that I could have obtained irrespective of the actions. So the maximum reward that I could get from state 2 is $6. Likewise, the maximum reward that I can get from state 3 is $9. The maximum reward that I could get from state 4 is also $9. And the maximum reward that I could get from state 5 is $12. Is that 9 for the, for the fourth state? It's actually 12. It's 12. So we have actually found the rewards for the 5 different states. Now that we have the rewards, we have to find the opportunity loss matrix. If you recall, the opportunity loss matrix Rij star is given by Rj star minus Rij. So what we'll do now is for every column that I have, now this has to span through all j's and all i's. So let's go one column at a time. So we pick column J, which could be 1, 2, 3, 4, or 5. So if we pick column 1, now I have to fill in these values by plugging in Rj star minus Rij. Now I know Rij across all rows for column 1. It is 3, minus 9, and minus 15. So I have 3, minus 9, minus 15. Now I have to subtract this from Rj star. In this case, it is R1 star because we are looking at state 1. So we have 3 minus the reward value that I wrote, 3 minus of minus the amount, 3 minus of minus 9, and 3 minus of minus 15. Now the second column of the reward matrix is 3, 6, 0, negative 6. So I would have 3, 6, 0, negative 6. And I would subtract the second reward, the maximum opportunity loss, which would be, or the maximum opportunity that I would have had would just be R2 star. So that would be 6 minus 3, 6 minus 6, 6 minus 0, and 6 minus of minus 6. Repeat the same thing for the third column. The third column, the numbers are 3, 6, 9, and 3. So write the reward values 3, 6, 9, 3. Then I subtract the opportunity that I would have had, the maximum possible reward, if the model ended up in state 3. And that value is 9, so I'd have 9, 9, 9, 9, minus, 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 minus. Now I do the same thing for the fourth and the fifth columns. In both of those cases, it is just 12. The maximum possible reward is 12. and I'd have to subtract the rewards from the reward matrix that we had already found, and those values are 3, 6, 9, 12 for the fourth column, 3, minus 6, 9 and 12 for the fifth column. That does not sound right to me. I believe that that is an error that has to be a plus 6. If you plug it in, you'd actually see that that number is actually a plus 6. I don't think that this mistake is something that was in the previous video and it actually happened due to editing somehow. That is actually a plus 6, not a minus 6. It just can't be minus 6. You could also verify this by plugging in I and j in our equation. J is 5 and I is 2. J is definitely greater than I, so the maximum that you can do is only 2. So 3 times 2, which is I, will give you 6. It's a plus 6. So 3, 6, 9, 12, 3, 6, 9, 12. So we would get 3, 6, 9, 12, 3, 6, 9, 12. Now that would result in our opportunity loss matrix. Now we call this opportunity loss because when we found our J star is the maximum reward that I could have had in my business, in my model, for a given state. Now, that is the maximum reward that I could have had, but if I don't choose appropriately, then my actions could either result in a profit or a loss. So what this matrix does is it kind of determines, or it exactly determines, the opportunity that you would lose if you choose the wrong action. And then we would minimize this opportunity loss so that we have a trade-off between profit and loss, and which is what we're trying to do. So 3 minus 3, the opportunity loss matrix is 0. 3 minus of minus 3 is 6, and that's 12, and that's 18. And 6 minus 3 is 3, 0, 6, and 12. 6, 3, 0, 6. 9, 6, 3, 0. 9, 6, 3, 0. So now that is my opportunity loss matrix. So note the dimension of the reward matrix must equal the dimension of the loss matrix. If it's not obvious here, you can see that they are of the same dimension, the reward matrix and the opportunity loss matrix. Now, we have to apply the Minimax rule for this matrix. So it's Minimax. So what we'll do is for every possible action, we're going to find the maximum opportunity loss. So let's find the maximum opportunity loss that I could have for every possible action. So the maximum loss here is the 9, the maximum loss there is a 6, the maximum loss there is a 12, and the maximum loss there is 18. And from this, now that I've found the maximum, I have to find the minimum, hence the name Minimax. So the minimum of these values, minimum of 9, 6, 12 and 18 is 6. But we are looking for the argument minimum over all i's, and we're trying to find the maximum across all states of the opportunity loss matrix, which is Rij star. You find the maximum over all states, and after you find the maximum, you take the argument minimum. I know that the minimum value is 6, but which argument or which action resulted in this minimum value? It was action 2. So, since action 2 is chosen, action 2 implies that you make 2 dozen cookies. So that is the decision that we obtain using the Minimax rule. Now, keep in mind the decisions sometimes agree across all rules, sometimes they contradict each other, but it's only natural that that should happen. But of all the rules, as I stated earlier, the Minimax rule is sort of optimal because it accounts for the opportunity that you would lose by choosing the wrong action, and at the same time it will try to minimize the loss that you would have. So you're trying to find the trade-off between not losing too much because you made the wrong chose the wrong action, or you chose an action that resulted in greater production but less sales, thereby increasing loss. So what the Minimax tries to do is it tries to find an optimal value or a trade-off point between the maximum profit and the minimum loss by using the regress matrix. So I hope that you understood the Minimax rule. If you don't follow it, I recommend that you watch the other two rules so that you can see the contrast between a Minimax rule and the Maximin and the Maximax rules. The next rule would be expected value based rule, which would involve states that are not equiprobable. And thank you for watching.